Hello and welcome everybody. My name is Yannick Krivka. I'm a PhD student at ETH Zurich, and I would like to thank the organizers for giving me the opportunity to speak here as part of the NCNGT in 2021 conference about my work, and in particular about the IRS compactification of moduli space. So this is the first of two talks. In this first talk, I want to introduce the objects that will be of interest to us, and then only in the second talk I will talk about a concrete description of the IRS compactification of moduli space. So for today, I will really focus on the basic objects, which will be, of course, what is an IRS, and also what the moduli space is, and at the very end, I will construct the IRS compactification for you. So let's jump right in. What is an IRS? So IRS stands for Invariant Random Subgroup, and I think that if you look at this combination of words for long enough and you have a little bit of a background in probability theory, you might very well come up with the correct definition of what an invariant random subgroup is. So let me try to give you an intuitive intuition, an intuitive definition that plays along these lines. So in order to talk about subgroups, we need a group. So let G be a group now, and let me first try to give you an idea of what a random subgroup should be. So a random subgroup of G should be a random variable taking values in the set of subgroups sub G of G. So now what should an invariant random subgroup be? So in particular, invariant with respect to what? So if you look at G and its set of subgroups, it's actually straightforward to see that G acts via conjugation on the set of subgroups. So it does make sense to talk about invariant random subgroups with respect to this action. Concretely, an invariant random subgroup can be understood as a random subgroup with conjugation invariant law. Okay, so now for those of you who have a little bit of a background in measure theory, know that in order to talk about random variables, we need to be a little more careful. So how can we actually formalize this? And in order to talk about random variables, which are usually measurable maps from a certain probability space into a certain target space here, sub G, we need a notion of measurability. And that leads us to a more careful analysis of the space sub G. Particularly, we would like to have a sigma algebra on sub G. And in our case, we will not just take any sigma algebra, but we will take a Borel sigma algebra, and the Borel sigma algebra induced by a certain topology on the space of those subgroups called the Chabot-T topology. This topology will also play an important role, although implicit, in our construction of the IRS compactification. So let me continue by talking a little bit more in detail about this space sub G with this Chabot-T topology. So the space sub G, because we would like to have a topology on sub G, and we will like to talk about topological groups in the following, not just about any groups. Let G be a locally compact second countable group for now on, and now in this topological setting, we would not just like to talk about any subgroups, but actually about closed subgroups. So from now on, we will denote by sub G the set of closed subgroups of G here. And now with this definition, we can actually give a topology on the space of closed subgroups called the Chaboty topology. But I will not define this topology explicitly here because it would take a lot of time. Well, maybe not a lot, but a significant amount of time. But I would rather give you two of the important properties that we will need in the following. So the first property, and maybe in fact the most important for us, is that the space of closed subgroups is in fact compact and metrizable with respect to this so-called Chaboty topology. And secondly, it turns out that the conjugation action of the group G on the space of closed subgroups is compatible with this topology. That is to say, G acts continuously on sub G via conjugation. Okay, so that's also very nice because we wanted to look at random variables that are invariant under this conjugation action. And now with these preliminaries, we're now in a position to give a formal definition of IRS, and this is as follows. An invariant random subgroup of G is a conjugation invariant Borel probability measure on sub G. So, okay, now at the beginning, I talked informally about random variables taking values in the space of closed subgroups. What happened now is I identified these random variables with their law, meaning their induced measure, and I said, okay, this is my definition of an invariant random subgroup. That has the advantage that these probability measures form a topological space on their own, namely with respect to the weak star topology. And this is, in fact, what plays an important role in our construction of the IRS compactification. More to the point, it is not hard to see that the space of invariant random subgroups, IRS of G, is in fact compact as well with respect to its weak star topology. So how do we see this? This is not very hard. So either you appeal to Prokhorov's theorem and or to Banach-Alaoglu's theorem. Both of them rely on the fact that the space of closed subgroups is compact, which again, as I said, is one of the most important properties that we will use, and this goes in here very crucially. And so it turns out that on a compact metric space, the space of probability measures is always compact as well. And now we're interested in the subspace of conjugation invariant probability measures. And because being conjugation invariant is a closed condition, this forms a closed subset and is therefore a compact space as well. Okay, so that was my introduction to invariant random subgroups, or at least their definition, but of course we would like to see some examples. So where do IRSs actually come from? And there's a rather large source of examples coming from probability measure preserving actions, meaning that if I have an action of my group G here on some probability space X, I can naturally cook up an associated IRS. And that makes also sense with respect to the informal discussion at the very beginning of this talk, namely, if you want to obtain an invariant random subgroup, you need to have a way of sampling subgroups at random, right? And in this setup here, there's a very natural way of doing this. Namely, you can just sample points in X with respect to this probability measure nu here, and then look at their stabilizers. And this will give rise to the so-called stabilizer IRS. So in fact, if you write this down more formally, you look at the map step that goes from X to the space of closed subgroups, which associates to every point X its stabilizer subgroup, and then you push the probability measure nu here. You push nu to another probability measure on the space of closed subgroups, and because the action here is measure preserving, turns out that this this image measure, this push forward, is in fact an IRS of G. Okay, so this looks like a very specific construction, and therefore it's quite interesting that it turns out that this is the generic setting, meaning that whenever you have an IRS, you can find some PMP action of your group such that your IRS comes from this construction here. And this is a theorem due to Aber, Klasner, Virac in the case of a discrete group G, and to these 7 people, Aber, Bergeron, Biringer, Gelander, Nikolov, Rembo, and Samet, in the locally compact case, which is the case we will be concerned with. So, okay. Now there's a very important special case that I want to consider in more detail. Namely, I want to tell you how you can see lattices as invariant random subgroups. So assume that you have a lattice in G. Recall, a lattice is a discrete subgroup such that the quotient has an invariant probability measure. More to the point, if you have such a lattice, then your group G acts on the homogeneous space G mod gamma via this action here. And more importantly, there is a unique invariant probability measure, which we'll call mu gamma, on the quotient G mod gamma. This here is precisely the definition of what it means to be a lattice. So now that means we do have a PMP action of G, namely on G mod gamma here. And we can do our construction from before and look at the associated stabilizer IRS, meaning look at the stabilizer subgroups. And it turns out that in this case, the stabilizer of such a coset gamma G is just the appropriate conjugate G inverse gamma G here. So plugging this in to our previous discussion, we obtain the following stabilizer map, which I give the name phi gamma in this special case, which sends this coset to the stabilizer, meaning this conjugate, and pushing forward our invariant probability measure nu gamma here to the space of closed subgroups, we obtain our associated IRS nu gamma. And I want to stress that this kind of construction, or this way of thinking about lattices as IRSs, turned out very fruitful in the theory of invariant random subgroups. And in fact, many results about lattices in Lie groups generalized to IRSs of said Lie groups. For example, there's a version of the Borel density theorem for invariant random subgroups, or the Kazhdan-Margulis theorem. But it's actually quite interesting because this construction can also be used to compactify the moduli space, and this is in fact Gelander's idea, who first came up with this construction, and this is the goal of this first part, to explain this construction. But before we go there, let me introduce to you the moduli space. So what is the moduli space? For me, the moduli space is always the moduli space of finite area, hyperbolic surfaces. And in order to talk about the space, one usually first fixes a topological model for our hyperbolic surfaces. That is, we look at topological surface sigma, which should be oriented, possibly with punctures, but no boundary components for us at the moment, and a negative Euler characteristic. And now it follows from the uniformization theorem that any such surface is hyperbolic, meaning it admits a hyperbolic structure, in fact, of finite area, and not just one, but usually a whole moduli space of such structures. And that gives rise to the definition of the moduli space, meaning the moduli space of finite area hyperbolic surfaces homeomorphic to sigma, or equivalently hyperbolic structures on sigma, is just the set of isometry classes of such hyperbolic surfaces with finite area that are homeomorphic to sigma up, yes, isometry classes, so up to isometry. And for those of you who haven't seen a hyperbolic surface yet, these look somewhat like this. So you can see here we have genus 3 and also 3 punctures. And note that because we have finite area, or we're considering the case of finite area hyperbolic surfaces, these neighborhoods about the punctures get very, very thin as we move to infinity here. Usually one calls these things cusps. Right. Okay, so much for the definition of the moduli space. Before I continue, I want to make a certain convention, namely from now on, because I'm looking at the moduli space, as you will see later, I will denote by G the group of orientation preserving isometries of the hyperbolic plane, which is isomorphic to PSL to R. So if you want, you can think about PSL to R in the following. How does this isomorphism come about? PSL to R acts on the upper half plane by a Möbius transformation, and some of you will have seen this construction. Okay, right. So how is the moduli space actually connected to this to these IRSs that I've been talking about before? In fact, the moduli space is connected to certain lattices in G. And in order to understand this, let me give you two observations, or this understanding is based on two observations. The first is that for every hyperbolic surface, we can find a lattice in G such that this hyperbolic surface is isometric to the quotient H2 mod gamma. Okay, so you can already see we can, given a lattice, given a hyperbolic surface, we always get a lattice. And moreover, because we are, remember we're looking at isometry classes, whenever you have two isometric hyperbolic surfaces in the moduli space, then there is an isometry between the two, which naturally lifts to the universal cover, meaning the hyperbolic plane here. And in fact, this isometry conjugates gamma 1 to gamma 2 here. Okay? And equipped with these observations, we can arrive at the following observation or proposition, if you will, So there's, in fact, a one-to-one correspondence between the moduli space of finite area hyperbolic structures on sigma and a certain and the set of conjugacy classes of certain kinds of lattices that works as follows. So you send the conjugacy class of gamma to the quotient H2 mod gamma. And of course, because we're only considering a certain topological type, here we need to consider a certain type of lattices, namely those lattices that are such that the quotient H2 mod gamma is homomorphic to the topological surface sigma. Okay, now for those of you who know already a little bit more about the moduli space, the moduli space comes already equipped with a certain topology, if you will, as the quotient of Teichmüller space. And also the left-hand side here comes with a certain topology, namely this space of lattices is a subspace of the space of closed subgroups. And I can mod out the conjugation action to obtain a quotient topology here. And however, both topologies are the same via this correspondence, meaning this map here is in fact a homeomorphism. Okay, so with this identification of moduli space, we can now embed the moduli space in the space of invariant random subgroups of PSL2R. And how does that work? We simply send a hyperbolic surface H2 mod gamma to the IRS mu gamma, okay? And it turns out that this map is a topological embedding. And of course, here, a priori, it's not clear that this is a well-defined map, because here we may change gamma up to conjugation without changing the hyperbolic surface as discussed in my observations. But it turns out that the construction of mu gamma is in fact invariant under such conjugations, meaning that mu gamma depends only on the conjugacy class of gamma. And now it's very natural to define the IRS compactification, namely we just put the moduli space in the space of invariant random subgroups via our embedding Yoda and take the closure, and we define this to be the IRS compactification of the moduli space. Now, why is this closure here compact? Remember from the beginning that we said that the space of invariant random subgroups is compact. So taking the closure, we naturally arrive at a compactification of the moduli space. Okay, now we have a definition of the IRS compactification, but what is the IRS compactification? I mean, apart from the definition that I just gave you, can we sort of describe this IRS compactification? Can we make sense of the points in this IRS compactification? And this will be exactly the content of my second talk. Thank you very much for your attention, and I'll see you all hopefully in my next talk. Bye-bye.